Welcome to CEDA-Labz. Now, let's start with our next module, Module 4. In this module, we will study programmable devices such as ASIC, PLDs, FPGAs, etc. We have divided this tutorial in several parts. In this particular tutorial, we will study basics of programmable devices, their classification and their respective scope, advantages and disadvantages. So, come on, let's start now. What are programmable chips? Basically, programmable chips are the type of ICs which are customized, or programmed by the user, according to its needs. In these type of ICs, there is always the option of reprogramming, if any problem occurs. It means unless and until user is not satisfied, he or she can reconfigure it again and again. This programmable ICs are programmed to do specific function. So, these chips are also called ASIC. Moving on further, we will see what is ASIC. ASIC means Application-Specific Integrated Circuit. Basically, it is a type of IC, which is designed to perform some specific application. This concept started in early 80s. They are also known as custom IC, as they are customized to a specific application. For large volume production, the vendors go for ASIC. ASIC can be classified in two types, full custom ASIC and semi-custom ASIC. The semi-custom ASIC is itself classified in three parts: cell-based ASIC, gate-based ASIC, and programmable ASIC. Further, programmable ASIC can be of two types, PLDs and FPGA. This figure shows the ASIC classification, which was discussed in the previous slide. First is ASIC and then it to classification, full custom and semi-custom. Further, semi-custom is classified as standard cell-based ASIC, gate-based ASIC and programmable ASIC. And again, programmable ASIC is also further of two types, PLDs and FPGAs. The type of ASIC we are going to discuss is full custom ASIC. In a full custom ASIC, the designer will design all the logic cells and layout for new application. The designer will not use any predefined cell in this approach of designing. Each design is customized according to new specification. So, 90% of the cells in this type of designs are a first-timer. Now question arises why we go for full custom? Sometimes it happens for some new design, or in any specific application design process, the existing cell libraries are not available. This occurs many times. Sometimes delays do not match, or there will be part consumption problem or sometimes area problem. The available cells will not satisfy the design constraints. So in order to achieve design constraints, we go for full custom ASIC cells. This is the microscopic photograph of custom ASIC 486 chipset, showing gate-based design on top and custom circuitry on bottom. The advantage of full custom IC is that they offer high performance, low cost and small area. Whereas, the main disadvantage of full custom IC is that design time will increase, complexity of desired architecture will increase, cost also increases, and there's very high risk of success. Now, coming towards semi-custom ASIC, the semi-custom ASIC can be categorized into three types. One is standard cell-based ASIC, second one is gate-based ASIC, and third one is programmable ASIC. The first category we are going to define is cell-based ASIC. The cell-based ASIC uses pre-designed cells for making designs. In this type of designing, designer will just create an interconnection logic and we use pre-characterized cell for defining our desired logic. Standard cells can be placed anywhere in the silicon. According to customer needs, all the mask layers are customized in this type of ASIC. The advantage of cell-based ASIC is that this technique will take less design time compared to full custom design. Since we are using pre-designed cells, also the cost involved in this design is less compared to full custom ASIC. There are very rare chances of failure of design in cell-based ASIC. The design which are using standard cell ASIC are less complex compared to full custom ASIC, since we are focusing only on interconnections. There are some disadvantages of standard cell-based ASIC, such as low performance in terms of area, power and delay in comparison to full custom ASIC. The next category of ASIC is gate array-based ASIC. In a gate array-based ASIC, the transistors are predefined on the silicon wafer. These predefined patterns are also known as base array. The smallest element which is replicated to make the base array is called base or primitive cell. This type of array-based ASIC is also known as masked gate array. The designer chooses from a gate array library of pre-designed and pre-characterized cells. These logic cells are also known as macros. In this only, interconnection is customized. Automatic placement and routing are used to convert the macro-based design into a layout. There are three types of gate array-based ASICs: channeled gate array, channel-less gate array, structured gate array. The figure shows in the slide is channeled gate array. In channeled gate array only the interconnections are customized. There will be a predefined space between rows of base cells and uses these predefined spaces for connection. Manufacturing time in this type of ASIC is from 2 days to 2 weeks. The figure shown in the slide is of channel-less gate array. In this type of ASIC, there will be no predefined or defined spaces between rows of cell. For routing, connections are established over the top of the gate array device, as there is no free space between rows of cells in the device. The logic density of this device is high compared to channeled gate array ASIC. Manufacturing time in this type of ASIC is from 2 days to 2 weeks. The figure shown in this slide is of structured gate array-based ASIC, which is also known as embedded gate array-based ASIC. In this type of ASIC also, only interconnection have to be customized. Basically, it is a type of gate array-based ASIC, in which some portion of IC is dedicated to a specific function, like processor or memory. The embedded area either can contain different base cell that is more suitable for building memory cells. Again, manufacturing lead time for this ASIC is from 2 days to 2 weeks. Next type of ASIC category is programmable ICs. In this type of devices, the configurable logic are connected by programmable interconnect. Normally, they are known as programmable logic devices, that is, PLDs. The main use of PLD is that user can implement the digital logic in a single device. These programmable devices can be reprogrammed again and again. This makes them very productive for new implementation. These ICs can be programmed according to the needs, or more precisely say, according to the specification of user. If any problem occurs during configuration, then the design is again reprogrammed. There are many advantages of programmable ICs, like as fast turnaround time, low cost, low risk of failure, lesser design time, and low eco-cost. These are the advantages which make programmable ICs very attractive to the users. If we compare this programmable IC to ASIC, ASIC has larger design cycle time compared to programmable IC, that is, ASIC implementation of desired logic will take more time. ASIC is more costlier than programmable IC. It means more money is involved in ASIC. ASIC is fast performance and involve low cost if we go for large volume production of devices. For small or medium scale production, programmable chips are good. The programmable devices categorizes in 3 types. SPLD, this involve PAL and PLA. CPLD, combination of more than one PLA and PAL from CPLD. PGA, programmable gate array, also known as FPGA. Now moving on further to SPLDs. SPLD is known as simplex programmable logic device. This is the most commonly called programmable logic device. Basically, in this type of programmable devices, the cells are in the form of AND/OR gates. These are personalized by making or breaking connection among the gates. The logic in SPLDs is in sum of product form. The basic architecture of SPLDs is shown in the figure below. In SPLD there is a plane of AND gates, followed by a plane of OR gates, There are three types of basic SPLDs: PAL, PLA, PROM. Now, if we compare the three PLDs as shown in the table, the first row consists of PAL. In PAL, array of AND gates are programmable, whereas array of OR gates are fixed. The second row consists of PLA. In PLA, both the AND array plane and OR array plane are programmable. The third row is PROM. In PROM, the AND array plane is fixed, whereas OR array plane is programmable. In this slide, all the type of SPLDs, which we discussed in the previous slides, are in the block diagram form. The programmable plane in each PROM, PLA and PAL are shown by blue color and fixed plane are shown by pink color. Next type of programmable IC for discussion is ROM or PROM. Read-only memory. ROM is a device in which data should store permanently. For burning data in this memory, engineers use a device called programmers. In ROM device, address line is input and data line is output. If we apply k number of address lines in a ROM, then in ROM output, we get 2 to the power k words each of size n bits. In the figure shown in the slide, it is shown that ROM has address lines as an input, and data lines as an output. Basically, when user gives address lines as input, then the data stored in that address location will be the output of ROM. In this slide, two symbols are shown in the figure, which are related to ROM. One is conventional and other one is array logic symbol of ROM. ROM circuit consists of decoder and OR gate. In the designing of ROM, or for implementation of ROM, we need a truth table as an input. In the truth table, 1 represents the connection, and 0 represents the open port. Mostly, ROM is used for the designing of combinational circuit. The designing will be clear in the next slide, when we'll describe an example. In the given example, we have to design a ROM for a circuit, which accepts 3-bit number and generates an output binary number, which is equal to the square of input numbers. Based on the information, we derived the truth table. In the truth table, we take a 3-bit input numbers, in the form of binary. Also, based on the input information, we draw the output truth table, which shows the square of input number in terms of binary. As you can see from the table, in the third row, if we consider input values, which are denoted by A2, A1 and A0, the input 2 is represented by 0, 1, 0, and square of 2, which is 4, is denoted by 0, 0, 0, 1, 0, 0, which is written in column B5, B4, B3, B2, B1, and B0. Like this, we write the square of numbers from 0 to 7 in the truth table. Now, during designing, it is seen that column B1 in the input section does not contain any 1. B1 column is always 0. So, there is no need to generate this column. It is also seen that B0 column is equal to A0 column. So, there will be no need to generate column B0 also. So, in the design, column B2, B3, B4 and B5 will be generated. As ROM have 3 input or 3 address line input, and 4 output lines, so size of ROM will become 2 to the power 3 cross 4, or we can say it is 8 cross 4 as it is shown in the figure also. In the diagram, it is shown that all the ones in the truth table are shown by cross at the output of decoder, and all the zeros are open, that is, no cross at the output of decoder. I hope it must be clear to you. There are 4 types of ROM: mask-programmed ROM, programmable read-only memory ROM, that is, PROM, erasable programmable ROM, that is, EPROM, electrical erasable PROM, that is, EEPROM. The next type of programmable IC we are going to discuss is PLA. The first category comes under SPLDs is PLA. PLA stands for a programmable logic array. PLA consists of AND OR gate planes. Both the AND OR planes in PLA are programmable. PLA is a type of programmable device, or SPLD, which is normally used to implement only combinational logic circuit. logic function is implemented in the sum of product form in PLA. In 1970, Texas Instruments developed first PLA. The first PLA, developed by Texas Instrument, is TMS 2000. In programmable logic array, the circuits are implemented in terms of sum of product form. In the diagram both the planes are shown, and planes as well as OR planes. Both the AND OR planes, in programmable logic arrays are programmable. In this slide, programmable logic array diagram is shown. As you can see from the diagram, in the input section, inverters are present for inverted input function. Some AND gate inputs are connected to non-inverted, some to inverted inputs and some are opens. Those connections, which are not required, are blown up or open, and those which are required, are connected. In the output section, the OR plane is present. The planes which are required, are connected and the planes, which are not required, remains open. In this diagram, it is shown that all the AND planes and OR planes are connected through wires. Normally, in PLA implementation before programming, all the connections are available. In this slide, as you can see that some connections are not there in the figure, and some are present. During the programming of programmable logic array, all the unwanted connections are blown up and only the required input connection remains. Let's discuss PLA implementation by taking one example. Suppose we want to implement function f0 that is equal to ab plus a bar, b bar, and function f1 which is equal to c, d bar, plus c bar, d into PLA. So, we have to implement two functions f0 and f1 in PLA. In the diagram shown here, there is a plane of AND gate and plane of OR gate. Initially all the connections are present. The established connections are denoted by crosses shown in the figure. When we are establishing the connection, first we will make connection of f0 function. For establishing AB, in first row of AND gate, there is a cross mark against A and B. Similarly for establishing the connection A bar, B bar. We put cross mark on second row of AND gate, against the inverted connection of A and B. The output of first OR gate is f0 function. Similarly, it is designed for f1 function also, as you can see from the figure. In the diagram against the left-hand side area of AND gate, first row of AND gate consists AB. Second row of AND gate consists of A bar, B bar. Third row of AND gate consists of C, D bar, and fourth row of AND gate consists of C bar, D. This is another example of PLA structure as shown in the figure, in which all the 6 functions f1, f2, f3, f4, f5 and f6 are implemented. On the diagram crossmark establish the connections. There are lots of advantages of PLA, which make them very useful and popular. First is, design checking is easy in PLA. We can check our desired functionality very easily. Second advantage is, it is easy to change the desired design. Layout of PLA is very simple and easy as compared to other random logic network. Also, layout designing is not a time-consuming task. We can implement any new technology in the PLA. The other advantages of PLA are that, designer is concerned of only connections. There is no need of any logic designing as compared to other gate network. This saves a lot of time and, design time is less as compared to other designs. Also, PLA implementation involves less cost compared to other implementation. Now, each and every implementation has some disadvantages. First concern is, speed. The designs implemented in PLA has less speed compared to other logic network. The area involved is large in this implementation. If we go for a large chip production, PLA and ROM are more costly than other random network. The size of PLA compared to ROM is always small if we want to put same functions in these programmable devices. As PLA has the ability to take don't care conditions into account, as compared to ROM, so size of PLA is small compared to ROM. Since ROM can take all the combinations of product terms. Therefore, ROM is used as a more general-purpose logic device for combinational logic compared to PLA, which doesn't have all the combinations. As PLA architecture is simple, due to this microprocessor design uses many PLA for their different operations like address conversions, decision tables, bus priority resolvers and indifferent control logic. For a new product design, PLA is always a good choice. Why? This will be clear in next slide. If we compare PLA to full custom design, then the design time in PLA is very small compared to full custom. The design will take few weeks in completion as compared to full custom, where it will take a year. PLAs are preferred in designing control logic as designs don't take too much time. We need to change only few connections. The next type of programmable logic device we are going to discuss is programming array logic. PAL stands for a programmable array logic. It is a type of programmable device wherein plain is programmable, whereas or plain is fixed. In PAL, we can implement small logic circuits, but for large circuit implementation, we don't prefer PAL. Programmable array logic can be used as an alternative of PROM. The logic is implemented in the form of sum of product form in PAL. But compared to PLA, PAL is easy to program as we have to program the only AND gate matrix. As compared to PROM, PAL uses less number of logic gates. So, PAL is preferred in comparison to PROM. In the diagram, the basic structure of PAL is shown, which consists of AND gate plane and OR gate plane. Here in this slide, there is a table of BCD to gray code converter. In the table, left-hand side consists of 4-bit binary input values, from 0 to 10, and in the right-hand side, their corresponding code in gray form is shown. We are going to understand its logic implementation. In the previous slide, we saw that there are 4 output functions during conversion: W, X, Y, and Z. Similarly, there are 4 input variables, A, B, C, and D in table. Each column of output is a function of input variables A, B, C, and D. So, we draw 4 K-maps for each of W, X, Y, and Z. We will solve the shown K-maps and generate the output functions W, X, Y, and Z in terms of A, B, C, and D. The output logic function W, X, Y, and Z are shown in the figure. As each AND gate generate product term. So, we burn each product term as shown in the figure. The connected connections are shown by cross. Each output function W, X, Y, and Z is shown by OR gate. The connections for respective OR gate functions are shown by dot in the figure. There are many advantages of PAL. First, PAL device consumes less board space compared to PLA and PROM. Less number of PCBs are required for PAL. PAL device doesn't consume much power compared to PLA and PROM. PAL device implementation doesn't require large costing and designing. Reliability of PAL device is high compared to other SPLDs. PAL devices have high speed, and they are more secure compared to PLA. So, low production cost involved in PLA devices. PAL is more flexible. PAL devices are easily modified. In PAL, both combinational as well as sequential logic is implemented. Compared to ROM, PAL can have large number of input ports. So, what we learned in this module? A quick recap. We studied about programmable chips. We studied ASIC and its types in detail with their advantages and disadvantages, all the types of semi-custom ASIC in detail. Moving on further, we learned about Programmable IC and PLDs. And then, in detail, we studied ROM, PLA and PAL.